Alrighty, guys. So still in section 2.2, part 3. Still discussing limits. Just going to look at another style of function, what we're going to call an oscillating function. Okay. So up top, some of you guys, hopefully everyone's familiar with a good old sine graph, right? So here I call this guy f of x is sine of x. It's just a wave, right? So just a wave going out here. So I didn't put too many coordinates on there. The key thing to realize though is that the maximum of sine graph is 1, and then the minimums are -1. Right, so this is just a wave that's sort of bounded. It's just bouncing between, or in math we say oscillating between the values of 1 and -1, and smoothly taking on all values in between as they do that. Okay, so some of you may have seen in pre-calculus or in previous classes this function. If you haven't seen it before, it's interesting. This is one that you might want to graph on. Actually, a graphing calculator is good for this one because graphing calculators start from the left and kind of work their way, and you can sort of watch this thing unfold. If you graph it on Desmos, it might be a little bit quicker. Might just appear. The book kind of does a better job of showing this function, I think, than I can do with a marker. But I'll try to explain what you're seeing and why you're seeing what you're seeing in the book. But check the book out. I'm pretty sure some of your WebAssign example questions have this idea too of what's called a oscillating functions. Some of you probably have those fans in your house that kind of rotate back and forth, right, as they blow the air, and they call those things oscillating fans. So oscillating is kind of just bouncing back and forth between two states or two values. So the way this function works, first of all, let's describe what we're seeing here. This guy's a wave, right, and it has what we call sort of a period. It's got sort of a certain frequency that it just keeps, it remains constant, right? So the distance between this peak and this peak is the same as the distance between this and the next peak, and so forth, right? And as x gets larger, as x goes out to infinity, this graph just keeps oscillating, just keeps bouncing around, right? Not too crazy. What is this thing going to do? When I put the 1 over x inside the sine function, I compose those two functions, in other words, what's that going to do to the graph? Well, in the previous video, we mentioned that this 1 over x as the graph, we call the reciprocal graph. And what we're doing here is taking the reciprocal of our inputs. So what the reciprocal does essentially is it takes really, really large numbers, and if you divide by a really large number, you get a really small number, right? And if you take a really small number, which we're going to be doing here, and divide by small numbers, you get a really, really big number. Okay. So, yeah, so we've got that. So what's that worth? Well, if we go back to the regular sine graph, as x gets larger and larger and larger, the graph just keeps repeating these waves, right? So you could say there's sort of an infinite number of peaks and then an infinite number of let's say, minimums and then an infinite number of maximums, and it just keeps on going forever. So there's an infinite number of these waves out to the right there on this graph, okay? As x gets larger. And at some point, x is going to pass 1. Right? 1 might live around here. So as soon as x passes 1, then we've got an infinite number of peaks and an infinite number of valleys. Well, what this thing does, 1 over x, is it basically takes all the numbers that are bigger than 1, and when you divide by all those numbers bigger than 1, you get a bunch of numbers smaller than 1, and vice versa. So what that's going to do is it's going to take all the x values for a regular sine graph, meaning all these peaks and all these waves, the infinite amount, and basically rotate. It's going to switch this graph around, take this portion of it, and fill it right there for all these values between 0 and 1, if we can see that. And it's going to take this little piece of the graph and put in everything past 1. And so that's kind of my description of how that function works. Hopefully that makes sense a little bit. Again, if you've got access to a graphing calculator, especially kind of an older, slower one, maybe put some dying batteries in there so it goes slow. What you're going to see is the graph's going to sort of come like this, right? And it should be around a height of 1 at some point, and then kind of dip down to its -1, and then back up to the +1, right? And that's like one wave. That's maybe this wave right here that we see. That's happening. And then we're going to have the next wave. But what's happening is it's getting squashed in here, right? There's going to be an infinite amount of these oscillations in just this area right here, or just this distance. And so what happens is these peaks get closer and closer and closer together, and what you end up seeing kind of just looks like a big mess, right? Kind of like a barcode or something. So you can't really see what's going on in there. I got to be careful when I'm doing it by hand to not end up doing stuff like this, right? Where I kind of backtrack here or like that, because then we're kind of violating our vertical line test. So anyway, I'm trying to do my best, but that's basically what the graph looks like. So kind of a big mess. All right. Okay, so let me get rid of the regular sine graph. That was just that reference. And let's consider this graph G, this oscillating, this sine of the reciprocal. First of all, G of 0. What's G of 0 would be the y-intercept of this thing. Well, it looks like I got a big mess of the graph approaching. Here's my y-axis right there. Coming from the left, coming from the right. But G of 0, how do I know that doesn't exist? Because G of 0 would be sine of 1 over 0. And that input doesn't exist even into the sine. So here we've got a DNE situation. Okay, so there is no y-intercept to this function. Can I talk about the limit? So it seems like from the left and the right, the functions are kind of doing the same thing, right? They kind of have that bouncy behavior from both sides. So I don't know that we really have to worry about the discrepancy between left and right. However, if I write this, the limit as x approaches 0, let's just consider from the right. The problem here is, and again, you probably know where I'm going when I erase that equal sign, is this, as x gets closer and closer to 0, so let me get rid of the other side of this that I put up there. Look at the original piece we had. As x gets closer to 0, as the graph moves this way, remember there's an infinite amount of these waves right here, these humps. I can't draw all of them, obviously. I'll be here for forever, infinite. And you just can't see it though, right? The thickness of this pen prevents me. But we can imagine that happening, right? If you zoom, this is another fun one to look at on Desmos. Well, I said that earlier, but zoom into it on Desmos and you'll see that the more you zoom in, it looks more of the same. You'll just see a bunch of more hills, and then you might zoom in closer and you'll just see more of the same. So it's kind of fascinating. Is it really true to say that the value is trending anywhere? No, right? Because as I get this close to 0, maybe the height's up at 1, right? So maybe I would say, oh, the limit's 1, it's going towards 1. But as soon as it hits 1, then it jumps back down and goes back to another -1, right? So maybe the limit was that, but it can't because it just keeps bouncing and bouncing and bouncing and never really settling down on anything. And so I'm going to claim that this limit does not exist. Okay, and again, so these oscillating functions, can an oscillating function ever have a limit that exists at some point like that, where the things are sort of collecting? Maybe. So you might see, or we will see some perhaps down the line. In my pre-calc class, I know I like to show those because they're kind of fun. So maybe we'll see one coming up, but yeah, something to think about. Okay, so that ones are a little bit tricky, but do your best with the web assigns, and there we go.